last class, what we saw was how we can specify orientation using just 3 parameters. In the way we were specifying orientation and position earlier, we were using 12 parameters. And we know that a rigid body requires only 6 parameters to specify position and orientation. So out of 12, there are 6 parameters which are dependent on the other 6. So it turns out that what we use for orientation is that orientation matrix, which itself has 9 parameters, out of which 6 are dependent, 6 are redundant in a sense. So we saw how Euler angles can be used in order to specify orientation with just 3 parameters, and we are now we started looking at fixed rotations about fixed reference frame axis in order to specify orientation parameters. I'll just sketch out that again and go on to the next topic. So about the fixed frame x, y and z axis by angles, let's say alpha, beta and gamma, right? So let us start. Let's call this x1, y1, z1. I'll be doing the rotations and sketching it in a slightly different way than I did yesterday, so that it becomes a little more clear. Fine. So we assume that the body reference frame is coincident with the global reference frame to start with, and we rotate about the x-axis by angle alpha first, right? So if we do that, the body, the z-axis rotates in this direction, y-axis in this direction by alpha in order to give you the new position of the body. Now instead of doing that, I am going to rotate the fixed reference frame with respect to the body reference frame by angle minus alpha about x-axis, right? If I do that, z-axis will go here, y-axis will go here, right? So the new z and y are here, x remains where it is. So I call this as y2, z2, and this is the same as x2. Fine. So now here, which is the global reference frame and which is the body reference frame? Yeah, x1, y1, z1 is the local reference frame now. x2, y2, z2 is the global reference frame. Fine. So this way I need to use just one figure to show all the axes. So now I look at the next rotation, which is about the global y by angle beta. Fine. So global y is now y2. I rotate that by angle beta, by angle minus beta instead of beta. Fine. So what I get is, so y2, so this goes here, is at 3. Don't worry about the sense of rotation. Basically remember that this x1 axis, or rather x2 axis, will go somewhere. So we need to only see them separate. So this is x3 now, this is z3, so y2 and y3 are the same, right? y1 is this. Okay. So now which is the global reference frame? x3, y3, z3. Fine. And which is the local reference frame? x1, y1, z1. Right. And now for the third rotation, which is gamma. So with respect to the z axis of the global reference frame, z3, you rotate the rest of them by angle gamma. Instead of that, I rotate about z3 by minus gamma. Right. So if I do that, z4 remains here itself, right, and x3 will go to x4, y3 will go to y4. And now the rotation matrix which corresponds to the local to global. Which is the local and which is the global now? The local is x1, y1, z1, and the global now is x4, y4, z4. The rotation matrix that we are talking about from local to global is what? Is from 1 to 4. Right? So based on the notation we have given, this is 3 to 4, 2 to 3, and 1 to 2. Fine. And so what is 4 with respect to 3? Sorry, 3 with respect to 4, not 4 with respect to 3, 3 with respect to 4. Yeah, that is the rotation gamma about z axis by angle gamma. So r about z by angle gamma. Fine. And 2 with respect to 3 is about y by angle beta, and 1 with respect to 2 is about x by angle alpha. Fine. So if you have this notation, if you have this way of specifying orientation, the corresponding rotation matrix of local with respect to global will turn out to be simply this. Fine. Any questions here? Won't it be? No, see, the local frame here is 1, right? One moment. Which is the local frame? 1, right? And the global frame is 4, right? So rotation, the rotation matrix of local with respect to global is the reference frame 1 with respect to reference frame 4, because 4 is global and 1 is local, right? No, this alpha, beta, gamma. Look at the last one we did, which is about the z frame, that is z3. Fine. We rotated to shift y2, y3 to y4 and x3 to x4. Fine. That is by rotating with minus gamma, right? But we are now talking about 3 with respect to 4 and not 4 with respect to 3. If it is 4 with respect to 3, it is minus gamma. Because it's 3 with respect to 4, it is gamma. Okay. So fixed frame rotations also can be done in whatever sequence you want, and you can give some notations for these angles, and you will get a valid representation of rotation. Fine. This final thing will turn out to be an orthonormal matrix. Now a third way or a different way you can specify rotation is to do the following. The rotation of a body about a point, whatever be the set of rotations you give, the final position with respect to the first can be obtained by a single rotation about some axis. Fine. So if you have a global reference frame, and if you have some axis, let's say u, about which you rotate by angle theta, fine, you will get the new position of the reference frames. Let's say small x, small y, small z. You can imagine the x, y, z reference frame to be fixed to the body, and so the body has displaced from coincidence with the global frame to the new position. So now the entire rotation is specified by two parameters, u and theta. This seems to be an even shorter description of rotation. No, because there are three elements in that u vector, of which only two are independent, because it's a unit vector. And so imagine u to be a unit vector, and then the angle theta is the rotation by which you give about this unit vector. So there are four parameters here, out of which three are independent. Okay, so it should be possible to determine this if you are given the local to global rotation matrix, right? And it should be possible to do the reverse also. Given these two, you should be able to find this. So this is an exercise. Try to work this out. It is quite useful to do that. Yeah, I'll give you just one hint. Look at two positions of the rigid body. Fine. Imagine that the rigid body is initially coincident with the global axis, and now it is rotated, and the reference frame has gone to the small x, y, z. Fine. Now if you look at the two positions of the rigid body, most points would shift from their original position to new positions. What about the origin? It will remain where it is. In addition to the origin, there are a set of points which remain where they are. Yes, along the u vector. So that is what we call the axis of rotation. Right? So due to this transformation, local to global, multiplying let's say a vector in the local frame, you get the vector or the position itself, because the origins are coinciding in the global frame. So these can represent positions of points themselves. Okay, there are points which remain where they are. So if you use that fact, you can immediately get u. Okay, so you try to formulate that and try to determine that. Yeah. So you are giving the answer. So I suggest that others also think about it and try to. You are pretty close to the answer. Yeah. Fine. So try to do this yourself. Now I would like to go back to our original definition of the inverse and forward kinematics problem. If you look at your notes, we have defined it in a particular way. Fine. The forward position problem is given the fixed parameters of the mechanism and the joined variables, determine positions and orientations of odd links. Fine. So we have been defining position and orientation. And the inverse problem, given the fixed parameters of the mechanism, position and orientation of the end effector, determine values of the joint variables. Fine. So let me take a case where we need to specify, find out the position of the end effector in a specific problem where we need to manipulate objects. We need to take an object from some place to another, and we need to specify, we need to find out how to specify the position and orientation of the end effector for that, so that what we have been dealing with, what we have been covering would be illustrated by a very clear example. In order to do that, in order to make it a little simple, I'll introduce a concept which will make the notation of finding out new positions, and if we have a sequence of displacements, the notation for representing position and orientation a little more compact. Fine. This is something we'll be using fairly frequently. After doing that, I'll take up the example. So if you again, let me draw the axis. Let's say this is x1, y1, z1. You have the local frame somewhere here. So y2, z2, x2. So this is the point O2, the origin, and this is the point O1. Okay. The transformation of a point, let's say P, in this reference frame to its global position is given by x of P, y of P. In reference frame 1 equals the location of the origin of this reference frame in this frame, that let's call it x O2, y O2, z O2, again in reference frame 1, plus this rotation matrix which takes vectors in 2 to 1, multiplying the local coordinates of the point P. So this is how the transformation of positions of points take place. Now I can express this in a slightly different way. Fine, using what are called homogeneous transformations. This particular vector, each vector or position of points, I represent by a 4-dimensional vector. Fine. So instead of this, I write it as xp1, which represents not p1 but the coordinate of p in 1, x coordinate of p in 1. So similarly yp1 is at p1, and I add the number 1 here, which is necessary for making the transformation compact. Fine. 1 has to be kept there always. So this is the extended 4-dimensional vector of this 3-dimensional vector. Then there is this transformation, then this multiplies the local coordinates, Fine. Now here the elements of this matrix are the rotation matrix and this offset. So here you have the 3 by 3 rotation matrix. So this portion is the 3 by 3 sub matrix of this 4 by 4 matrix. This 4 by 1, this 4 by 1. Okay, these elements are 0 and this is 1. Fine. This column is this particular vector. XO2 in 1. So pardon my suffixes. Fine. So I can write this as, now remember this transforms the locations of points. So we have this as the local coordinates of the point and this as a global coordinate of the point. Right? So let me call it P in coordinate in reference frame 1 is equal to this transformation matrix, which is 4 by 4 taking 2 to 1 and P in 2. Fine. And this has the property that if you want to express some k with respect to I. So remember this transformation matrix contains the information about position and orientation because it has the rotation matrix and the offset of the origin, right? So that contains, now that could be specification for position and orientation. So position and orientation of the kth body with respect to the ith body can be obtained from an intermediate transformation of the jth body with respect to the ith and then the kth body with respect to the jth. This actually makes the chain multiplication very compact. If we didn't have that and we had used this non-homogeneous form for the transformation, then what would happen is that this particular translation term will actually build up into a very large set of terms, which is cumbersome to deal with. So this becomes more compact. Fine. This build up is going to occur right there in the columns here, but you don't see it when you write it. When you don't expand it, you don't see it. So there is some amount of economy in notation. Just try to see what this would be if you are given k with respect to I. From that, how do you find out I with respect to k? You know the elements of this. From that, how do you get the elements of this? You can do this as an exercise. This is the inverse of this, by the way. One is the inverse of the other. Fine. So this notational convenience is necessary for us. You have taken down. Now let us apply what we learned to a specific problem. So there is a table. on which there is some part placed. This has to be picked up and put on and assembled onto this part. So here this particular part I will show in detail later. But it has 3 pegs. This is something we had seen earlier. It has 3 pegs, and those have to go into holes here. Now, with regard to dimension, positions and dimensions, let me give the edges at the corners some names. So let this be the corner A, B, C and D. Let me show this part in more detail. If you look at it from side in this direction, what you will see is the following. This is the corner A, as well as behind that D, and this is the corner B and C. So there are these specs which are there below the body. Okay. If I see it from above, so this is the corner A, B, C, D. So there is one peg here, another here along the same line parallel to this edge, and there is a third peg here, sorry, here. Fine. So this is placed on the table with the pegs down. This has to be picked up and brought to this position and assembled. Fine. So here let me draw the outline of the part when it is assembled. So this corner is A. So this corner is B, C and D. Now this is essentially the operation. Now let me use a reference frame to locate things. If you use a global reference frame like this, okay, needn't be along this. So we'll call it x1, y1, z1. The location of A fine. The location of A if I locate the, if you consider this point to be A, so let me draw a line through this and through this and call this particular point as A. Fine, is that clear in the figure? So if I call that point as A, then xa1, the specification of the problem is that xa1 or xaya is that A in reference frame 1, which is a global reference frame, is given as 300, 400 at an elevation 500 from the base of the, all in millimeters, let's say. So I am talking about the point in contact with the table, right? The point which is in contact with that, there is actually no material point there. Imagine that it is in contact with the table. So that is this. Okay. Now I also give the following information. The angle that this edge, this is an inclined plane, this is horizontal, these two edges are horizontal. The angle that this makes with the x-axis is, let's say, 30 degrees. Fine. And the angle that the inclined plane makes with the horizontal is 15 degrees. Now if you look at A in this particular reference frame, so let me call it, I'll give numbers based on the way I worked out, so you will see that a little later. I'll call this the x4 axis, and the y4 axis is horizontal in this direction, and z4 is perpendicular to both of them. So origin of this, that is this corner of the inclined plane, that is O4, with respect to the global frame, is given in addition to these angles. So x04, y04, z04. So that point is on the x1 y1 plane. So that's given. These two angles are given. The angle made by this edge and this particular inclination, those are also given. Now in addition to that, you are given a few more things. Or rather, let me ask, what else needs to be known? Orientation of what? Of the object. Yeah. So BA edge is along y1, the AD edge is along x1, right? That's the way it has been oriented in the first position. Second position is for you to work out. Okay. So what we now need to do, a few more specifications have to be there. I mean, you try to work it out, we'll work it out. What needs to be done is a gripper has to come, pick up the part, right, and take it to this position and to a position where you can now push into assemble. And what you need to do, if you remember the joint interpolation discussion in this class, in this course, the input for that to determine how the joints should move are certain locations of the end effector, right? From that we use the inverse kinematics problem to work out the corresponding joint angles or the joint variables, and those form the inputs for calculating this interpolation. So what we are trying to do here is specify the position and orientation of the end effector at whatever convenient points which are necessary to pick up this object and place it here. The set of points or set of positions and orientations the end effector has to go through. So we have to take certain decisions. For example, how would the end effector pick up this object? So let us look at the object a little more. This is on a table, right? So a gripper will come. Let's assume the gripper is has two flat faces, which can be closed, which can be brought together. So we can take it to the top of the object and close the gripper to hold the object tightly, right? So how will you place this? So on top of that the robot hand is there, the robot arm is there, the rest of the robot will be there, fine. Now how do you pick it up? So let me show it from above also. Fine. The width and length of the piece are, let's assume, known. So 50 millimeters and 100 millimeters. Remember, what we need to do is locate these pins, these specs on top of the holes. We need to do that finally, right? So how do you place, how do you pick it up? There are many ways of doing that. Now think of some simple way. I can pick it up with one of these sides of the grippers touching this and the other on the other side, or touching these two faces, right? If I try to hold by the edges, it will not be firmly held, right? So I can bring the gripper on top of this, right? How far down? Shouldn't be below the lower edge, right? That is assuming that when you push it in, the lower face will be flush with the top face of the part on which you want to assemble. That may not be the case. The peg may be longer than the hole, fine. So you may be able to bring down further down, but it is safe to keep it at up to here, right? This is a place you can locate. So the gripper could be like this, the robo further up like this, fine. So if you look at it here, you will see it the gripper coming down like this, okay. Now in order to specify the end effector position and orientation, after the object is gripped, we need to know the relationship between the object and the gripper, because what we know are the initial and final location of the object and not the end effector. So after the gripping is done, we need to know the relationship between the object and the gripper, the end effector, in order to be able to say where the end effector should be when the objects are at these two positions, right? So that is why we need to decide on how to grip. Okay, so let me fix a reference frame to the object. Fine. If you look at it from above, let this be x2 and let this be y2. The z-wise location of the corner is here, right? So this is one way you can fix a reference frame. You can do it whatever way you want. It is not really very important, provided you define it very clearly, right? Now this particular gripper, once it grips, also has a reference frame attached to the gripper. Let me consider it to be the sender, at the center of the gripper. So the axis fixed to the gripper, x3, y3, fine. And here perhaps it's a good idea to put the origin of that reference frame at the edge of the gripper, fine. So if you do that, then this is the z3 axis and this is the y3 axis. So now we can decide what should be the location in this direction to grip the object. What will be that direction? The location of this particular origin, which is a reference frame fixed to the gripper, in this direction is fixed, because if you put it at the center of the gripper, that will be at the center of the object when the gripping is done, right? Since this is 50 millimeters from this edge, this particular point will be 25 millimeters from this edge. Now if I center it in this direction also, this will be 50 millimeters from this edge, right? So now I can specify the position and orientation of the gripper reference frame, that is the end effector reference frame, with respect to the object reference frame as follows. What are the coordinates in the x direction? This is with respect to 2, fine. So let me use curly brackets. What are these? We have centered it, right? So what is the x direction coordinate? 25. Y direction? Is it direction? No. So height of this hasn't been specified, right? So we'll say that this is, we need this height, let's say 10 millimeters. Okay, so 10. What about the orientation of 3 with respect to 2? would it be the identity matrix? So all you need to do is look at the x3 vector in the second reference frame. What are its coordinates? Right? The y3 vector in the second reference frame. Sorry. And then z3 in second reference frame is 1. So it is aligned. It is aligned with the second reference frame. So the identity matrix is the rotation matrix. So position and orientation of the fourth reference frame with respect to the third reference frame with respect to the second is given by these parameters. Fine. So now my question, what all do we need to know in order to do this operation? Fine. So let's go back to what we drew earlier. The object is placed here. It's A, the coordinates of the point A in the global reference frame 1 is given, right? The other thing we know is the coordinates of this particular point, which is one edge of the inclined plane in the global reference frame, and we know directions of two of the edges. So we haven't worked out the coordinates of this reference frame, the position and orientation of 4 with respect to 1. That is something we can do given this information, right? Is it required? That's one thing. The other thing is where will this reference frame 2 be? Reference frame 2, which is attached to the object B when the object is in the first position. That is something we can work out, right? Because we have attached reference frame to the object, and we know the object in the first position, right? So the orientation matrix of 2 with respect to 1. 2 is the reference frame attached to the object with respect to 1 in the first position of the object can be obtained, right? That is R 2 with respect to 1 position 1 of object, in position 1 of the object. 2 will go somewhere else when the object goes here, right? That we will have to work out later. So what is this? I'll have to bring back and show this partially. So there is the x1, y1 is one reference frame, and when we look at it from above in the xy plane, we see this. Okay, so x2, in which direction is it aligned with respect to the global reference frame? Is parallel, but in the opposite direction, right? Is in the negative x1 direction, correct? So this particular first column would be, what would it be? -1, 0, 0. Fine. Now similarly, if you look at y2 in this direction, y1 is in this direction, they are parallel but is in opposite directions. So you have 0, -1, 0. What about z? Z2 and Z1, same direction. So 0, 0, 1. So that is R2 with respect to 1 in the first position of the body. Okay. Now if we can get the position of this particular point A in the global reference frame, right, and the coordinates and the directions of the reference frame when it is assembled, then our job is done. We have all reference frame at appropriate positions and the transformations. Now we can simply do a transformation to get the positions that we want. Okay, so let us construct that. These are exercises you have to go through if you want to really specify even the position of the end effector. Fine. So now we have this inclined plane. We have put some reference frame already on that, x4 in this direction, y4 along this edge, but origin being here, and z4 perpendicular to, one moment, the way I have fixed probably was different. Okay, I had fixed y4 along this edge actually, so let's not consider this. So this is y4 along one of the edges of the inclined surface, okay, not the horizontal surface. And then perpendicular to both of them you have z4. Okay, and now when the body is placed here, your x2, y2, z2 which is attached to the body will be aligned along this. So I'll call that new position as x5, and this is y5, and this is z5. Okay, and in this frame, this corresponds to A, and the two holes that you have are here. The three holes that you have are here. Okay. So finally, when the object is placed here, this x5, y5, z5 have to coincide with the body reference frame x2, y2, z2. Fine. If that is done, you will see that the holes get aligned. Okay, so we have to find out the position and orientation of this reference frame in the origin, in the global reference frame, and for that we can actually do it through this particular reference frame x4, y4, z4. So we have to know the origin of this particular point, which we have already specified. If you remember, this is O4. We have specified the global reference, the global coordinates of the point O4, which is the origin of the fourth reference frame, as 200, 400, 0. So let us now work out the orientation matrix. R4 with respect to 1. So if you look at this, you will see that it consists of 3 columns. The unit vector along x4, the unit vector along y4, and the one along z4. These are the 3 columns, but each of them expressed in the global reference frame. Right. So what is x4? The unit vector along x4 in the global reference frame. I am talking about this reference, this particular vector, and if you remember, our x-axis like this, and this angle was given as 30 degrees. Although it doesn't look like that, it is 30 degrees. Fine. Now, what are the coordinates of this? Right? Cos 30, sin 30 is 0. What about y4 unit vector? Y4 is along this. What about its z coordinate? This is 15 degrees, by the way. Z coordinate is sine 15, right? The z coordinate of, remember, the z axis is along this, fine. Z1 axis is along that. So what about its what about the z coordinate, z1 coordinate of this y4? That is sine 50. What about its horizontal component? The vertical component is sine 15, horizontal component is cos 15. So you have two cos 15 components here, which further gets projected onto the x1 and y1 in those directions. So this is 30 degrees with respect to x1, this is 30 degrees plus 90 degrees, this edge, right? The projection, the cos projection of this unit vector onto this is simply along this, fine. So that has cos 30 plus 90 and cos 15 into sine 30 plus 90, fine, with respect to the this is the y1 projection, this is x1 projection. You can easily see that this is a unit vector and this is the y4 cap vector, fine. So now what about z4 cap? You can do the same thing, project and find out, but you can also get it through both in one, fine. So this also, so you need to really find only two. You can get the third from this cross product, okay. Yeah, no, I said it can be specified by 3. I didn't say we need only 3, because in order to do the transformation we need all this, fine. So it can be specified by 3 or 12, or depends on what we use to specify. So if you look at it carefully, you will see that we have used really only 3. Why do I say that? Look at the way I specified this particular reference frame. The orientation, the way I specified, really I have used only 3. Try to figure that out. Okay, now we have got 4 with respect to 1, so we should be able to get this, right? What about 5? Finally we need 5 with respect to 1, right? So we can get 5 with respect to 4, and then we can get 5 with respect to 1. What is this? This is identity matrix, right? So I 3 by 3 identity matrix. But is that enough? I need to also locate it. So I have to know with respect to this edge and with respect to this edge, what is the location of the point A, right? So I need to also know, so this being reference frame 5, we have O5. So x O5 y05 z05 in this reference frame 4. That is the easiest way to specify it, right? Or at least one easy way of doing that. So I had given some values there. Slight change in values, so I'll give values here. This is 200, so this is something you have to work out numerically. Fine. 400 0. I had actually given it as earlier 4 with respect to 1, which is not correct. I have some other numbers for 4 with respect to 1. I'll modify that now. You have taken this down. Position of 5 with respect to 4 is 200 400 0. And we are out of time, suppose. Yeah. So 4 with respect to 1 is 500 800 0. So you will work out the inverse kinematics of this later. So work out this numerically. Fine. I suppose we have given everything that is required. Fine. I could have done it in slightly different ways. I could have, instead of this, said that these points are at these particular locations, right? So then working out is a little different from this. Instead of that, I gave it very conveniently, saying that when placed, the point A will be at this particular point, which is easier to specify. Okay. Fine. Now the exercise is find out the location of the end effector just before gripping at the first position, and find out the position of the end effector when just before we are going to push the pegs into the inclined plane. Okay, and I think we have specified enough to get to that. We can use the homogeneous transformation matrices for calculating it. Multiplying 4 by 4 matrices it takes time, so you can do it on computer very quickly. Fine. So complete this exercise. In the next class, let's see what the answers are.